In this screencast, we'll briefly discuss the problem of formalisms and computations. So on the left, on the one hand, we have formalism, and so this is supposed to be an egg. And on the other hand, we have computation, and let me put this computation inside of a chicken. Well, my rendition of a chicken, anyway. And I hope that the meaning of these symbols will become clearer momentarily as our screencast proceeds. So this is the chicken. So in order to formally reason about computations, we need a formalism. Okay. But in order to have a formalism, we need to have some precise a priori concepts of what sort of computation that formalism will be describing, will be helping us to describe. And this brings us to a very important and fundamental, one of the fundamental questions in theory of computation, not just in theory of computation, in computer science. What comes first, formalism or computation? And this is at the heart of what is known as Church's thesis. Sometimes it's called Church-Turing thesis. So let's briefly talk about that thesis. So let me drop the picture of a master. The master actually formulated this thesis onto our whiteboard. This is Dr. Alonzo Church. Let me write it down. Okay. This is Dr. Alonzo Church. There's an excellent Wikipedia article about Dr. Church documenting his contributions to the theoretical computer science and biography. But he's primarily known for his development of lambda calculus, a formalism for defining functions that actually forms the basis of functional programming languages such as Lisp and Scheme, and so it can be used to define all sorts of recursive systems, not just individual functions. And so Church's thesis, simply put, all right, this is a common sense formulation, is that everything computable can be computed by a formalism X. Right. Sometimes it's stated as everything computable on natural numbers can be computed by a formalism X, and X can be replaced with lambda calculus or Turing machine, or some other formalism, such as programming language L, which is the formalism developed in the second chapter of the great book Computability, Complexity, and Languages by Davis, Weyuker, and Segal, and which we will develop in later screencasts right, on the theory of computation. So an implicit assumption in this thesis is that there must be a device that can mechanically, that's the operational word, mechanically execute computational instructions expressed in X. So the next important question, and that is, why is this a thesis? Well, it is a thesis because we cannot prove it as a mathematical theorem. Why not? Because of its circular nature. You can prove things that start from primitives and build up on primitives and become theorems and so forth, right? But here, this is not the case. And what's the circular nature? We cannot develop a formalism without some a priori notions of the computation that we're interested in capturing. And but in order to reason about the computation, we have to come up with a formalism. So it's sort of formalism and computation must grow side by side. One cannot be entirely expressed in terms of the other. So let's talk about an important problem of choosing a formalism. So suppose that we have some ideas of what sort of computation we want to express, some ideas about the formalism. So there are objective factors and there are subjective factors. So objective factors is, suppose that we have several formalisms, right? On the objective side, many formalisms that operate on natural numbers have been shown to be equivalent. What does that mean? Well, let's suppose that okay, we want to show that we have f1. Somebody has shown that f1 is equivalent to f2. Formalism 1 is equivalent to formalism 2. Well, what does that mean? So that means that any computation expressible in terms of formalism 1, right, can be, right, this one can be performed and will produce the same result as the computation, the same computation expressible in formalism 2. Right. So to make this more concrete, well, let's suppose that we have implemented breadth first search in Python and in C++ and in Java. Right. So we have three formalisms, but and they may use different data structures and different underlying representations, but they will produce the same results. Given the same input, they will have the same output. But then there's let me illustrate the subjective part of choosing a formalism, and that is that, well, people always have individual preferences. And so let's suppose that we have this piece of sheet music, right? That this music can be played on a rock guitar. Right, so let me drop a rock guitar. But it can also be played on the classical violin. So let me drop the picture of the classical violin. Right? Essentially, we have the same computation specified in that sheet music, and two different formalisms and two different devices in which those formalisms can be executed. Right? So which one is better? Well, that's up to the listener, the listener's individual preferences. And I'll try to put some links to the same piece of music played on the rock guitar and on classical violin, and let you decide which you like best. And another objective factor, which is low-level formalisms and high-level formalisms. Let me also illustrate it through an example. So this is a very simple robot. It's called Junun Mark III robot. Junun Mark III robot, which is okay. So let me write it down. Junun Mark III robot. It has the 16F84A chip inside. Well, this model. And that chip can be can be programmed in 16F84 assembly. That's an assembly language for that chip. Okay, I forgot an A here. AA. Okay. Now here's an example. On the left hand side we have an assembler code, and it doesn't do anything complicated, but pretty hard to figure out what exactly is going on. And on the right hand side we have a higher level programming language which we can use. It's JAL, just another language, which we can use to program that robot. And JAL, I guess, is a lot more understandable to us. It's a Fibonacci number function than what we have on the left-hand side. at least for the purposes of programming the robot. So here's another important insight from this. Whatever formalism we choose, it must be reasonably. What's reasonable? Well, that's up to us and to the task and to the nature of computation we're trying to express. Must be reasonably high level to make formal reasoning about computation easier, not harder. If we think too much about the formalism, then that's probably not the right